Hey everybody, welcome to our video on supervised classification in QGIS. It's the moment we've all been waiting for. We've had a lot of videos talking about the theory of supervised classification, and now we're going to show you how to actually do the steps in QGIS. So what we're going to do today, we're going to create a band set. We're going to compute the means of each input band. We're going to use those means to assign band weights and actually rescale. We're going to define training input, and then we're going to run some of the classification algorithms. So there's a lot you need to know before you get to this point. If you're new to this, please check out these videos on basics of multi-band rasters, basics of reflectance and spectral signatures, intro to classification, intro to supervised classification, and in particular this textural classification video where we made some of the inputs that we're going to use right now. Also, a little advice before we start out. Although we've gotten in the habit of converting from digital number into radiance or reflectance for many applications, for classification it's not so important to actually convert away from digital numbers. That's because classification really relies on parsing pixels based on their relative spectral signatures, whether they're relatively the same or relatively different. And because radiance and reflectance are basically linear transformations of digital number, it doesn't really change much as far as the classifiers are concerned. And we're going to rescale them anyway by normalizing them. So we don't need to convert away from digital number. Another word of advice, classification can and often should involve more than just multispectral images. So in this video, we're going to try to include a textural image or two. You could also include elevation data, principal components. We're actually going to do this in the next video on unsupervised classification. And also temporal differences. So you could, subtract a January raster from a June raster to look at seasonal differences and then include that as a classifier, right? So lots of creative things you can do with classification. And finally, it's essential to rescale your inputs. We had a video on this previously, and we're going to show you how to do that here in this video. So let's get going. We've got a QGIS project open. Our aim here is to create a classified map of Yellowstone National Park using this 1989 Landsat TM image. You can see this is after the big wildfires, so many forest areas are burned. They're showing up here as these kind of brown or dark areas relative to the green unburned areas. Then we've got a lake here, we've got some rhyolite here, and some mountains, Rocky Mountains over here. The other thing we've done in the previous videos is we've computed these textural metrics. So we've got uniformity, contrast, correlation, entropy, and matrix of correlation. So we're going to probably include a couple of those in our classification today. Now, unfortunately, our first step is to create a band set that we can use in classification. But because we're trying to kind of mix and match inputs, we're going to need to add everything to the band set as single kind of grayscale bands. So we're not going to add multi-band rasters. So because of this, actually, what I'm going to have to do is go and actually add the original Landsat layers as individual bands. So we'll quickly go do that, and then I'll pause the video and come back. Okay, so we're back, and I've now added bands 1, 2, 3, 4, 5, and 7 of this 1989 Landsat image. One thing you can see is that these are much larger than the clipped images we had been working with so far. But we're not going to worry about that right now because we're going to be able to use a mask, an analysis mask, during the classification. So right now we're just going to add these into the band stack as they are. And let's look at that. So to start the classification process, we're going to use the SCP plugin. If you haven't installed it yet, you need to go to Plugins and install it. If you have, you'll find the menu item here, and we'll show the plugin. And initially, I expect you'll have nothing showing up in your lists. One thing you can do is hit this refresh button right here, and that's now going to bring in all of our Landsat bands and also all of our textural bands that we had created earlier. Alright, so what do we want to add? Well, we definitely want to use bands 1 through 7 of our Landsat image. Okay, so we're going to highlight those and hit Add. and they're all going to show up down here in our band set. Then let's also pick, why don't we pick entropy and matrix of correlation as our two textural. And you can add as many as you want, but I just don't want to overdo it. So we're going to add those. So those are now at the bottom of our stack. So this band set's going to be treated as one big virtual raster layer during the actual analysis. So now that we've defined our band list, the next thing to do is going to be to define our scalings or our weights. So we're going to go to Basic Tools, this next tab, and I think if we go over here, right here, Band Weight. So here's our bands, and right now they're all weighted the same. So before the classification algorithm is run, they'll all be multiplied by 1. We want to put in some unique weights so that when they're multiplied, all of the ranges, the numerical ranges in every band become similar and comparable, so they have equal weight as they go into the classifier. So the way we're going to do this by normalization. We're going to end up dividing each band by its mean, okay? And we don't actually want to take the mean of all the pixels in the full Landsat. We just want to take the mean of the pixels that are in the classification area, which is really going to be just within this Yellowstone shapefile. So what we're actually going to do to get the means is we're going to go back to our previously clipped image where we had clipped just to the Yellowstone extent, and we want to know the mean for each band within this extent, right? So to do that, there's two ways to do it. One way is to use actually zonal statistics, and actually that might not be a bad way to do it. Why don't we show how to do it that way? So we'll use zonal statistics. So we're focusing on this tight clip here, and actually what we can do is we'll do it for each band individually. So we'll do it on band 1, okay? That's our input raster, and our vector layer is the Yellowstone UTM shapefile, and the column prefix is going to be, maybe I'll actually call it B1. That way we'll know it's B1. And we only really need one statistic, and that is mean. Okay, so we'll hit OK, we'll run that. Okay, so it's completed. I'm going to close, and then just to show you what happened, right-click over here, open attribute table, and now in the attribute table, we have the band 1 mean, 56.8, okay? So I'm going to now do that. I'm going to repeat that exact same process for the remaining Landsat bands as well as the entropy and matrix of correlation. So we're going to get a mean pixel value for all of our classification inputs. I'll pause the video and come back when I've done that. Great, so I've actually done that like 8 times now. It actually was pretty fast because I didn't have to close the zonal stats window each time. I just updated the things and kept running it again and again. So let's go check if indeed the attribute table has been updated, and it has. Here's all of our means. So we got B1, B2, B3, 4. Okay, so what I'm going to do now is try to just copy paste this row of the shapefile, and indeed if you just highlight it, clicking over on the left side, and then you hit Control C, it should copy. Take yourself to a fresh Excel sheet, right click, I'm just going to paste values, and it all comes in. The things that I'm interested in are right here. This is B1, B2, 3, 4, 5, 7 mean, entropy mean, and correlation mean. So now to compute my weights, I'm going to simply compute 1 over each of those means, okay? And those are my weights for B1, for each of the input layers. And so now my next job is going to be to go and actually enter those into SCP plugin. So I'm going to find my way back to the plugin here, and I'm going to update this weight column. And if you need to make sure you can see what you're doing, click here and expand it. And now you know which row corresponds to which band, and we're going to update the weights one at a time. So the weight for band 1 is 0.0175. And I'm going to go down and update the others and then rejoin the video. Okay, so I've now updated all of the weights. And again, these are multipliers that are going to be multiplied by each pixel in the given band. Notice that most of the Landsat bands, the multipliers are relatively similar, but the entropy band is much larger, as is the matrix of correlation. So if we hadn't done this, right, we would have really been comparing apples to oranges with the Landsat bands versus the textural layers. But now we're going to rescale everything or normalize everything so that all the values are pretty similar. So it is possible to proceed by staying in this SCP plugin. For example, you can go to, I believe, band processing and have access to some of these same tools, or band calc. But we're going to switch over to the SCP doc, which is over here. If the doc hasn't opened for you, you can always right-click and add it in these various toolbars. So what we're going to do now is actually begin to define our training polygons. And because this is supervised classification, we need to tell the computer what is the spectral signature of each class that we're interested in classifying. So what we're essentially going to do now is trace each of 5 classes. That's going to be water here on the lake, rock here on a rhyolite flow, meadow here in this green meadow, burned forest, and unburned forest. Okay, we're going to have 5 classes. And the first thing we actually need to do is actually create a training input file. This is basically a shape file, but it has a .scp extension that is going to hold each of our training polygons and I think the related spectral information. So the way to do that, make sure on your doc you're over here on the the training input tab, okay? Then click this button for create new training input. This is going to prompt you to essentially create a training shapefile. I'm going to call mine Yellowstone Training 5 Classes version 2. So have a meaningful name. All right, so now we're going to actually get these polygons, trace the polygons, and add them to this shapefile using this, which is the temporary ROI tool. So click this once, and then you can go ahead and start left-clicking your training polygon. The goal is usually, and then right-click to finish it, and there it is. So now to store that in our training input file, we're going to update any information we want to have in the attribute table over here. So we're going to call this class 1, and the info is going to be water. And we're going to leave it as part of macro class 1. And to add it to the training input file, you just click this button. It gets added into that shape file, and it also appears here in our ROI list. Okay, so now I'm going to repeat that process for rock. I'm going to go ahead and grab this big area of the rhyolite flow, and you should feel free to zoom in and check it out. I'm going to right-click. Now this is going to be class 2, and it's going to be called rock. And again, I'm going to click and save it here. So now we have our 2 classes specified. All right, now I'm going to add the remaining 3 classes and come back to you. So I've now completed the 5 training polygons. The 3 I just added were meadow, unburned forest, and burned forest. So here's meadow, unburned forest, and burned forest. And notice they each have a different class ID and a class info name. One thing I'll point out, if we now go to this training input file up here, first thing I'm going to do is actually double-click there on the symbol and actually change the fill to be transparent. And I'm going to change the outline to be red so that we can actually see through the training polygons. You can clearly see what you've captured. And a quick note is that I've tried to make the training polygons as big as possible, but careful to stay within the class of interest, but capture as big a variety of pixels as you can within that class, right? That's what's going to give you want to give the most robust training data that you can that captures the actual variability within your class. Otherwise, you may end up missing pixels during the classification. The other thing we'll do is we'll right-click up here on the training input file, open the attribute table, and you can see it now has these 5 features: burned, unburned, meadow, rock, and water. All right, so we're ready to classify now. We've built our input data, our band set. We've defined our training polygons. So still within SCP, the next thing to do is to highlight, hold down Shift and highlight, clicking on the left numbers here. Highlight all 5 ROIs, and then we can go to this button, Calculate Signatures for Highlighted Items. And if things are good, it's now going to generate the statistics in the spectral signatures for each of these training polygons. And then we can use them as an input to our classifier. Okay, so having done that, let's now take a peek. Notice it unhighlighted all these rows, so I'm going to hold down Shift and left click to highlight them again. And I'm going to actually go to this button, Add Signatures to Spectral Signature Plot. This will bring up, oh, it's beautiful, bring up and show us the spectral signature of each plot. Each line is a spectral signature, and the translucent envelopes, of course, are the error envelopes, reflecting the standard deviation on each band for each training class. We can also go down to the signature details here, and we can see that here are the mean values for meadow, the standard deviations for meadow. Here's the number of pixels that were in meadow: burned, unburned, meadow, rock, and water. So there they all are. And if you want, you can compute spectral distances in here, which is pretty cool. I think you use this tab to calculate spectral distances between them. Might as well just do it. Okay, so let's move on now to the classification. So we are going to close this window, the plot window, where we're able to visualize the training data. And we're now going to go back to here to this classification tab. Okay, and this is the money tab. So, and I will say you can accomplish a lot of this also from the main SCP window, but we're going to start out right now in this dock. All right, so we do not want to use macro classes. Remember, we defined all of our classes as classes, so we're going to use the CID as our input. We get to choose our algorithm. Let's start with minimum distance. We also get to choose a threshold. So the threshold units are different depending on which classifier you choose. And notice 3 classifiers: minimum distance, max likelihood, and spectral angle mapping. For this example, I'm only going to use the minimum distance, and I'll let you play around with the others if you like. But keep in mind, the thresholds are different for each of these. And so what is a threshold? It basically means if it goes to classify a pixel, and the pixel is not actually close enough to any of the training groups or any of the class means, that pixel will be left as unclassified. So if you set this threshold aggressively, you'll end up with a lot of unclassified pixels that didn't quite fit into any of the classes. If you leave this threshold at 0, all the pixels will be classified, even if they weren't necessarily well fitting into any of the classes. So if you're doing minimum distance, this threshold is a distance above which a class would not be, a pixel would not be classified. So if a pixel has a bigger distance than you define in the threshold, it won't be classified because it's too far from one of the means. If you are choosing maximum likelihood, this threshold becomes a probability, okay? And in that case, any pixel that is below a certain probability actually would not be classified. And spectral angle, this threshold becomes an angle from 0 to 90 degrees. And any pixel that's above your threshold angle, in other words, its vector is too far from the class vector, will not be classified. So keep in mind, these thresholds change a lot, and you got to know what you're doing. All right, so we're going to try minimum distance, and let's try a threshold of 0.5. So if a pixel is greater than 0.5 units from the class mean, it won't be classified. We're going to leave this alone. Now here's an important detail. We are going to apply a mask. This is so important because remember, we made our bandset using the full Landsat images. So we're going to apply this mask, which is our shapefile denoting the boundary of Yellowstone. So hopefully we're only going to get classified images within this mask. And we can generate a classification report if you are keen. And then you hit run, and you hope for the best. Oh, actually first you have to, so I remember that those are in there. Okay, now we just wait and see how it looks. Oh no, after all that, my classified image came out totally black. Oh dear, see, they all have a value of 0, which is unclassified. Okay, so in the end, to make this work, and I did get a classified image, you can see here. To make it work, I ended up setting the threshold to 0 so that it wouldn't discard any pixels, regardless of how well they fit or didn't fit. If you want to use the threshold effectively, usually it involves trial and error. Setting different thresholds until you start to see some pixels end up unclassified. But in this image, it ended up working out pretty well. One way to kind of convince yourself that it worked reasonably well is just to go back and forth with the Landsat image, and you can see it even actually managed to classify some of this river through here, which is pretty great. And in general, it's not a bad idea to have some unclassified pixels in your image, because it really helps to, especially with supervised classification, helps draw your attention to classes that you probably missed. Like, this image looks great right now, but in fact there's probably some bad misclassification going on in here. So I recommend playing with the threshold until you get some unclassified pixels in your image. Have a good one.